Good afternoon. My name is Dwayne Brown with the Office of Communications, and welcome to NASA headquarters. Today you will hear about the preparations, challenges, science, and much, much more of the upcoming August landing on the Martian surface of the most advanced rover designed by humankind. We'll also have the debut of one of the many education and public outreach tools for the public to experience the adventure of Mars exploration. To officially kick us off and set the stage for today's event, to provide opening remarks is 5-time flown space shuttle astronaut, astrophysicist, and the Associate Administrator for NASA's Science Mission Directorate. Please welcome Dr. John Grunsfeld.
Well, I'm just incredibly excited to be here. We are 20 days, 12 hours, 29 minutes, and 47 seconds from landing on Mars. MSL holds the potential to look for evidence of habitable environments, if they existed, on Mars in the distant past. The Curiosity rover has the potential to discover the building blocks of life on Mars, if life ever existed on Mars. This is just phenomenal that we have a rover that's this close to landing and over the next 2 years helping us to answer these questions. However, the Curiosity landing is the hardest NASA robotic mission ever attempted in the history of exploration of Mars, or any of our robotic exploration. This is risky business. Given that we are in the heart of summer, there's a real opportunity to achieve tremendous broad public engagement on this adventure on Mars. We're going to engage summer camps, science centers, our NASA centers, in fact, all around the world. People will be following the Mars Science Laboratory landing and the subsequent adventures of the Curiosity rover. 43 years ago today, the Apollo 11 mission launched to the moon. I hope the MSL Curiosity landing will be as memorable and exciting for kids today as the Apollo 11 landing was when I was in summer camp 43 years ago. And I remember it well, and it put me on a path that I've found very exciting, leading to me here at NASA headquarters in front of this distinguished panel, the best of the best. And I'm sure you're going to hear about the difficulties, the great science we expect, and the harrowing ride through the Martian atmosphere that is now 20 days, 12 hours, 27 minutes, and 53 seconds from landing. Welcome, and I'll hand it over to Doug McQuiston. Thank you.
Thanks, John.
Okay, before we hand it over to Doug, a few housekeeping notes. For the folks and the many folks out there watching us on television and elsewhere, you can follow the Mars mission, the Mars exploration program, and a host of other information on www.nasa.gov/Mars and www.nasa.gov/MSL. And yes, Twitter, Facebook, YouTube, social media, and the like. Follow us at Mars Curiosity. Join the conversation. There will be a lot of it starting today and beyond. The excitement is building not just here in the United States, but all over the world. Now, let's get started. Let me introduce you to today's speakers. First up will be Doug McQuiston, Director, Mars Exploration Program, NASA headquarters in Washington, D.C. Michael Meyer, Lead Scientist for the Mars Exploration Program, NASA headquarters. John Grotzinger, Mars Science Lab, Project Scientist, California Institute of Technology, Pasadena, California. Pete Tysinger, Mars Science Laboratory Project Manager from the Jet Propulsion Laboratory in Pasadena. And Jeff Norris, Manager, Planning and Execution Systems, also at the Jet Propulsion Laboratory. So hang on to your hat, strap on, and I'll toss it over to Doug.
All right, thanks, Dwayne. Well, just in case you missed it, we're 20 days from what could arguably be the most important event, most significant event in the history of planetary exploration. What's going to be fun, is we also have something at the end of this press conference that I think you'll like. It's a little unique twist we'll do here. I think you'll enjoy it. Mars Science Lab, most challenging mission we've ever sent to another planet, and certainly the most challenging we've sent to Mars. It truly is a major step forward, both in technology and in science, potential science return and science capability, to unlock the mysteries of Mars in places that have never been accessible to humankind in the past. Could I have the first graphics up? Thank you. This program, the Mars Exploration Program, was designed to create steady progress in both technology and scientific capabilities at other planets. Spirit and Opportunity to MSL, we've changed and significantly reduced the landing ellipses, so our landing accuracy is much higher. We've extended mission life. We've extended roving distances. We've made great strides in the potential science we can do with the instrument suite that's aboard. Our orbiters are no less important and interesting. We've gone from Odyssey to Mars Reconnaissance Orbiter, imaging capabilities dramatically enhanced, as well as the capability to return larger and larger volumes of data from the planet, both surface missions and orbital missions. These are very important tools to expand science and greater capability for the United States as well as the world in science. But with that capability expansion comes a need to land in a new way. So this is no airbag bounce that we're going to get here. This is a Viking-like landing, but with a twist. The engines are on top of this system instead of underneath it, so that it's easier to rove when we get there, in a technique called the sky crane. Is it crazy? Well, not so much. Once you get comfortable, once you understand it, it's not a crazy concept. It works. Is it risky? Landing on Mars is always risky. There are hundreds of discrete events that occur, from release of the cruise stage to parachute deployments to heat shield deployments. All of these are unique and any one could cause problems. We go from 13,000 miles an hour to 0 in 7 minutes. That's quite a challenge in itself. And then there's the unknown. There's Mars. Mars throws things at you. Dust storms, atmospheric density changes, wind. So it's a very unique and a very challenging environment. You're going to hear a lot more about the details of entry, descent, and landing from Pete in just a few minutes. But what I want to do is describe what it feels like. EDL, entry, descent, and landing, is like a game of dominoes. With the release of that cruise stage about 10 minutes before we hit the top of the atmosphere, that's the first domino that's been flicked. The long string of dominoes that follows, that are supposed to fall in sequential order, are all done autonomously, just like in entry, descent, and landing. If one of them is out of place, it's very likely that the last domino won't fall, which means Mars Science Lab, Curiosity rover, may hit the ground harder than we want it to. Remember, every landing is unique. Every landing is like a first. I'm incredibly proud of the team that's done this. They have done a fantastic job of testing systems, designing systems, obviously, and building them, but analyzing them and testing them, understanding the edges of the envelope, pushing them to their limits. They've done everything possible to ensure the success of this mission. There's always a few last-minute game changers. As an example, Odyssey lost a reaction wheel a few weeks ago. That was totally unexpected. Reaction wheels are utilized to help manage spacecraft attitude and momentum in space. We haven't fully worked out the issues related to that loss yet, but we have plenty of backup systems. Mars Reconnaissance Orbital will be collecting communications data. ESA's Mars Express will help us with that. Of course, there's the Deep Space Network. Odyssey right now looks like it may not be in the same spot that we'd expected it to be, so there may be some changes in real-time communication. We'll let you know as this develops. We still have more work to do. But keep in mind, there is no risk to MSL landing. It does not have an effect on that. It's important to keep in mind the communication. So in summary, NASA was created to take on big challenges, and that's what this one is. MSL is forging ahead in greater and greater ways for science and for technology. Robert Kennedy said, "Only those who dare to fail greatly can ever achieve greatly." MSL is poised to do great things. Come with us. Follow us with the rest of the journey. Meet us on the surface of Mars on the 6th of August. I'll let you hear the details from my colleagues. Michael?
Well, thank you, Doug. And for those who are having problems with the math, August 6th, 1:31 in the morning on the East Coast, the Mars Science Laboratory will deliver Curiosity to the surface of Mars. And it's to answer the big question, has Mars ever been able to support life? Starting with the landing of Mars Pathfinder in 1997, our understanding of Mars has basically boosted our concept that Mars has had the energy, the ingredients, and the liquid water that could have supported life. Over the last decade and a half of exploration, we have found more water than expected. We have found plains of water ice surrounding the poles on Mars. We have found the equivalent of buried glaciers at mid-latitudes. We have found modern-day reoccurring flow features that suggest brine. And we have found the minerals that have formed in water associated with specific periods of Mars history. We have revealed the planet with the resources to support life, and which has undergone a huge transition from a warm, wet, relatively neutral planet, then losing most of its atmosphere and magnetic field, to a cold and dry, acidic planet that we see today. With the landing of Curiosity, the adventure begins as we explored the past and present environments at Gale Crater. And to tell us more about Gale Crater, turn it over to John.
Thanks very much, Michael. It's my pleasure to tell you today a little bit about the landing site that we're going to explore. In the past, I've discussed all the exciting science instruments that we have on Curiosity, but today as we get ready for landing, I'd like to say a little bit to remind you about what we're going to be doing on our mission for habitable environments. Now, just so that everybody is aware of that, what we mean by a habitable environment is a place that has water, because all life as we know it depends on water. We need a source of energy because all microorganisms require some source of energy in order to live. And in addition to that, we need to identify a source of carbon, which may be the most difficult search that we have on this mission. All organisms as we know it are constructed of carbon. So that's what we mean by a habitable environment. So it's not just one thing we're after, it's several things, and we may find one here and one there. So this is going to be a mission that requires a lot of patience. And as a scientist, this is not something for which there is a slam dunk discovery, but many bits of information come together to build this, and it's going to take us a while to get there. However, we have a great place to do this. So if I can go to the first graphic, please. What we see here is the location of Gale Crater on a very important transitional boundary on the surface of Mars, where we go from the southern highlands, which are colored there in sort of the hot colors, going from reds down into yellows and then passing into blues. They give way to the part of Mars called the northern lowlands. And across that boundary, we think billions of years ago, water flowed across that surface and was present. And there's Gale Crater, sort of like a little bowl capturing any water that may have been present there. Gale is one of the lowest places on Mars, and if you don't know anything else in advance, that's where you want to go to find evidence of water. Water flows downhill, and that's where we're going. Okay, in the middle of that bowl, Gale Crater, which, to give you a sense of the size of the crater, it's about the width of the Los Angeles basin. And in the middle of it, we have a mountain that the science team has called Mount Sharp. And that mountain in the middle, notice again the color and the color scale. That mountain has 5 kilometers of relief on it. That's taller than any mountain in the lower 48 states in the US. So that's our primary exploration target as we head into the crater. Okay, so if I can have the next one, please. Here's a blow-up now of Gale Crater, and you can see Mount Sharp there in the middle of the crater, and there's our little landing ellipse. And I say little because Pete will show this in a minute, but one of the great science accomplishments already has been given to us by engineering, which is being able to get a landing ellipse so small that we can get into the very best places on the surface of Mars. Our final 4 landing sites were all top choices by the science community. None of them were excluded by engineering, and in the end, we had this very high-class problem of having to pick one of them, and we wound up with Gale. That's because of this small landing ellipse, so this is a tremendous advance for science already. So when we get down onto that ellipse, we check out the instruments, check out the systems, the engineering systems, and then hopefully in a couple of months we'll be on the road to the base of Mount Sharp. However, when we picked this landing site, we also wanted to make sure that there was something really good right in the ellipse, and the science team has been rolling up their sleeves in the last couple of months. And now I'd like to go to the next graphic, which shows the landing ellipse. Now it's in that yellow outline. And what you see in sort of the colors that are present there is this bright red patch that's very close to the center of the landing ellipse. That's the good stuff. If you have to pick a place to land on the surface at Gale Crater, that's where you'd want to go. And so again, the engineers in the last couple months were able to make the ellipse even smaller and squeeze it down closer to Mount Sharp, so we have a shorter drive to get to the mountain, but we also land right on some really exciting materials that we think may have formed in an aqueous environment. So if you look above the ellipse, you can see a feature in blue that's above the ellipse, and it kind of has a fan shape to it. That's a feature that geologists call an alluvial fan, a kind of a feature that we believe was formed by flowing water. And since we know that water flows downhill, that downhill direction is right where we're landing. So we believe that even where we land, when we have this long process that we'll have to go through to get ready to roll, we're already going to be able to explore some exciting science targets. So that's where we're headed, and we're excited about it, and I'll turn it over to Pete.
Thank you, John. Well, it's been a little over about 8 months since we launched Curiosity on its way to Mars on the 26th of November. And in that time, the cruise performance of the vehicle has been outstanding. We've really had no significant issues with the vehicle. We've been doing routine maintenance and checkouts. We've had no real equipment failures, and so we're in top-notch shape as we approach the planet. But now the payoff comes. The next major step to get to the science that John has described, the riskiest part of the mission is entry, descent, and landing. And if I can show the video, please. So 10 minutes out, we deploy the cruise stage and turn the spacecraft into the correct attitude to enter into the Martian atmosphere. The entry interface is about 125 kilometers above Mars. We toss a couple masses away, so we unbalance the vehicle. That allows us to turn the vehicle with a slight cant to its approach, a slight angle of attack, which gives us lift, and that goes into the ability to have the small landing ellipse that John referred to. We lose about 98% of our energy during the hypersonic entry as we dissipate energy against the heat shield, and then at about Mach 2 or a little bit below, we will deploy our supersonic parachute. This parachute is the same design, except slightly larger, than was used for MER and Phoenix and Pathfinder before. That deploys, as I said, at about Mach 2, and then when the spacecraft becomes subsonic, it drops off the heat shield at about 8 kilometers, and the radar turns on and begins to look for the Martian surface. Spacecraft continues to descend until about 2 kilometers up, when the descent vehicle drops out of the back shell, lighting its 8 Mars landing engines, and propulsively sends to the planet. When it gets down to about 100 meters or 150 meters above the surface, it will deploy the sky crane maneuver, where the rover separates from the propulsive descent vehicle, deploys its wheels, and the entire 2 bodies descend slowly to the planet. The vehicle also contains a descent imager, which will take high-resolution, 8 frame per second, high-definition quality pictures of the planet, all the way from the time when the heat shield comes off until landing. Here you see the sky crane maneuver with the mobility deployed, and we then land at about 1 meter per second vertical and a little bit less than 1 meter per second horizontal. When the spacecraft touches down, the descent stage senses the loss of weight, cuts the umbilicals, what we call the bridles, and the descent stage flies away in a controlled manner about ½ kilometer, where it is crashed somewhat gently into the surface, we do not burn the engines to depletion. And that leaves Curiosity on the surface of Mars early in the morning of August the 6th here in Washington, ready to start its science mission. If I could see the next graphic, please. This shows the ability, the capability that guided entry has given us. Guided entry has allowed us to reduce the landing ellipse to make it much smaller than it has been landing ellipses for Pathfinder, MER, and even Phoenix. The previous missions went into the planet ballistically. They entered the Martian atmosphere, and they fell like a rock, and the landing site was determined by errors in the navigation and density profile changes in the atmosphere that were not modelable, not predictable ahead of time. What MSL does is it flies out those atmospheric density variations, and so gives it a much smaller landing ellipse than previous missions. The MER ellipse you see just barely fit inside Gusev Crater, where Spirit landed, and would have no chance of fitting it inside Gale Crater. But with MSL, we're able to land not only on high-quality science material at the crater floor, but also close to Mount Sharp, where the science mission can begin. The science mission is going to proceed relatively slowly. This mission is extremely complex. The vehicle goes through a major set of configuration changes through entry, descent, and landing. And as a result, it will take some time for the engineers to characterize the mission, characterize the integrity of the vehicle at the beginning of the mission. We expect to get black and white photography in not our best resolution, but certainly good resolution on the first, second, and third days of the mission, and then thereafter. We expect to see scientific color photography starting about day 3, day 4 of the mission, and we should be getting some thumbnails from the descent imager looking at the descent starting about day 2. I think back to you, Doug.
Okay. Well, just like landing is a bold endeavor, NASA's pushing the edges of the envelope for public engagement with the Mars Science Laboratory landing as well. So we've got museum sleepovers planned. We've got obviously TV broadcasts through NASA TV planned, public events at virtually all the NASA centers, thousands of people on Facebook and Twitter that are following us, even a Mars as Art display that's going to begin its journey around starting at the Delaware House, which is a rest stop on the Interstate 95 Turnpike, which will be kind of interesting. We also have a lot of educational materials. One that we're particularly proud of is the first publication of a Mars-specific Braille book for the blind. We've produced 1,500 of these, and they're going out to organizations and associations for the blind around the country to utilize these. In addition to these types of things and websites in general, we've got a number of interactive experiences we've been working on to help you explore Mars, whether it's a new iPad app that just came out recently, which is a 3D app, to the Be a Martian app, which now applies to cell phones, virtually all of the operating systems on cell phones. You can get right in the action with the mission as it unfolds also, with the 3D interactive experiences developed through the Unity engine, which uses real Gale Crater terrain as well as a very realistic 3-dimensional rover in the setup of this. There's a website that's a one-stop shop for information and entry points for these types of things, games or information on the mission, and that's on the screen for some, but otherwise, mars.jpl.nasa.gov/MSL/participate. I encourage you all to go there and fiddle around, explore, and enjoy. Before I get to the main purpose of this part of the press conference, I just want to bring your attention to a couple of round things sitting over there next to Jeff. That's an MSL Scarecrow wheel and a Spirit Opportunity wheel. The Scarecrow wheel actually is well used. The Scarecrow is a test device that was used out at JPL, crawling over terrain and testing out how well the MSL system, the Curiosity system, would work on the surface. So please take a look at those as you go out and you get an idea of the expansion of capability and complexity we've been able to accomplish through a program designed like the Mars Exploration Program. So we have the pleasure to debut a new interactive experience with cooperation from Microsoft, which is working with us at NASA for new educational products. The next generation of learning experiences is actually arriving. bringing the challenge of landing Curiosity to every living room that would like to play in this game. Families can get a taste of the daring that's involved in this, just landing this mission on the surface. It's going to be very similar to the way the team actually is going to do that. In a way. So I'd like to turn this over to Jeff Norris to explain this and describe it. Jeff?
Thank you, Doug. So I'm very excited to announce a groundbreaking partnership between NASA, the Jet Propulsion Laboratory, and Microsoft to inspire the next generation of explorers and scientists and technologists. Mars Rover landing is the agency's first experience for a home entertainment console, and through it, we're bringing some of the excitement and a few of the challenges of landing Curiosity on Mars to living rooms around the world. As we're demonstrating live here today, people take control of their very own spacecraft using the Kinect and move their body to steer the rover through the stages of entry, descent, and landing. Right now, Danielle is playing the first phase of the game. She's doing her best to burn off some speed while staying on target and inside the entry corridor. In the next phase, she'll have to react quickly in order to deploy the parachute, separate the heat shield, and then release the descent stage at the perfect moment. It's not easy, but we think families are going to enjoy facing the challenges of landing on Mars firsthand. By the way, I'll mention that Danielle is the granddaughter of Apollo 14 astronaut Stuart Roosa, and quite literally an example of the next generation of explorer. We'll check back in just a moment to see how her landing is progressing. The Mars Rover landing game is free and available now on Xbox Live Marketplace. We have demonstration systems set up here at NASA headquarters and at the Jet Propulsion Laboratory for you all to try it out firsthand. It's exciting, challenging, and a whole lot of fun. Doug mentioned many ways that people can watch Curiosity's landing and get involved with the mission. In our mutual commitment to inspiring the next generation in science and math, NASA and Microsoft will also soon unveil a special destination on the Xbox Live dashboard dedicated to the Curiosity mission. In it, people will find pictures, videos, and more facts about the mission. And then on August 5th, NASA TV's live coverage of Curiosity's landing will be broadcast there too. Also coming soon is an educational experience based on Microsoft Kodu, in which students can program their very own Mars rover and make some discoveries of their own. Let's check back in with Danielle. She's finishing up the second stage of the experience now. She's deployed the descent stage, and in the third phase, she's going to have to perform the sky crane maneuver and then carefully manage the retro rockets in order to bring Curiosity down for a safe landing. This is a tricky balancing act, and we didn't give her a lot of fuel, so let's give her a minute to concentrate and see if she can land successfully.
We have rover separation. We have touchdown on Mars. We have a rover in Gale Crater.
On the real thing. But again, ladies and gentlemen, come with us, experience the Mars exploration, activity, and adventure. Now let's take some questions. We have questions starting here in Washington on our phone bridge, and we'll see if we have any questions before we come back here at our NASA Center. So you can please wait for the mic, give your name and affiliation, please. Denise?
Hi, Denise Chow with Space.com. I'm not actually sure who this is directed to, but anyone who wants to answer. I was wondering if you could talk a bit about what the mood is of the team. You've mentioned that this is a very tense 7 minutes, but is it excitement? Is it nerves? Is it a combination of both?
Pete, you want to take that?
Well, I think the team is very excited. They've come to the end of a long journey. Many of them have worked on this mission for 6, 7, 8 years. I think the team feels that they've done everything they could do to make this successful. That being said, success is not assured. We could have any one of different kinds of problems that could end up in a end of mission. But I think the team is very positive. Morale is good. They've been working hard, but I think we'll be able to give them some time off before landing. So I think that the team is really up for this. I think this is very much the mood of the team before Spirit and Opportunity landed. I think same kind of anxious anticipation with a little bit of nerves.
Any other questions here from Washington before we go to the centers? Oh, Denise, go ahead. You got a follow-up? And then we'll head to the Kennedy Space Center.
Just a follow-up for John. What kinds of experiments or science will be done before the rover starts moving towards Mount Sharp? You mentioned that there's some very interesting materials there.
Yeah, I think we'll see when we get there, but with all this great data that the Mars program gets these days, we can do a better job in advance of sort of guesstimating what we might encounter. And we're hoping to find materials that interacted with water, maybe even were transported by water. And so as we check out the instruments, we'll be able to take full color, high-resolution panoramas and a level of detail unprecedented in previous missions. We'll be able to use the ChemCam laser very early on to get a sense for the composition of what's there. We'll be able to turn the DAN instrument on and look for water that might be in the subsurface materials or including the rocks and minerals. So even though we have this long period of checkout, it is punctuated by what we call intermission, where the science team has an opportunity to drive the rover some relatively short distance to move up to materials that we think are promising, so that when we do the second half of the commissioning activity period and we deploy the arm and reach out and start to touch things, we're doing it in a place that we think will have a lot of excitement. So it all sounds like a long time to check out, and it is, and we need to do it, but we will be getting a lot of science on the way.
Okay, we're going to transition down to the Space Coast at the Kennedy Space Center for questions. Kennedy?
Hi, it's Irene Klotz with Reuters. I have two questions. The first is for John Grotzinger. The red stuff at the base of Mount Sharp in the landing ellipse, does that signify some mineralogical or some compositional, or is it what is that? What does that red stuff symbolize?
Yeah, so the red stuff is present where we land, and it's also at the base of Mount Sharp. And we don't really know what that material is. The property that's being mapped there is something called thermal inertia, which is its ability to retain heat. And so at night, when that's imaged, you can see the ground sort of glowing. And what that tells us is that there's probably harder material there. And the harder material suggests maybe that there could have been water that interacted and maybe precipitated minerals there. So we can't guarantee that, of course, but that's one of our hypotheses going into it. It could be other things as well. It might be lava flows, but based on the whole geological context, we're pretty optimistic to find something that has to do with water.
Another question from Kennedy?
The communications at all, as far as the time delay or when you all would be hearing what happened?
Irene, could you repeat the question?
I'm sorry, do you need me to repeat the question?
Yes.
Thanks. You mentioned about the Mars Odyssey glitch, and you said it shouldn't impact landing, but will it have any impact on the communications plan for understanding what's happened during landing?
I can do that. So to be clear, it won't have any impact on landing. It's all a communications issue. So there are a number of assets there. Mars Reconnaissance Orbiter will be recording the entire event from entry in the atmosphere all the way past the landing time itself. So it will collect all that information. it is a store and forward, so it will record it and send it back to us sometime later, a few hours later. Odyssey was going to see all of the landing to the end, and it is essentially a bent pipe, so it just sends that data back. It has moved in the orbit from where it was originally, and so we are assessing what the issues are there, how much it's moved, and whether we want to try to move it back. There's a potential it won't see all of that landing area from a communications perspective. It won't cover the entire landing event at this point, and it may not cover any of that landing event. We just need to find out once the team is finished with their analysis. Deep Space Network will cover it. Mars Express, that belongs to the European Space Agency, will also cover it. But those both lose coverage due to orbital geometries about a minute to 2 minutes before landing itself. So there's no impact to landing itself, no effect on MSL. It's simply how the data gets returned to us and how timely that data is.
Another question from Kennedy?
Not know beyond the 14 minutes whether it landed safely or not?
Right.
If I could expand on that a little bit.
Sure.
So the spacecraft will transmit what we call X-band tones. If those of you familiar with Spirit and Opportunity, it's exactly what was used on Spirit and Opportunity. And as Doug pointed out, the landing site's not visible from Earth at the time of landing, and so those tones will cease to be received at Earth sometime between the time the parachute deploys and the heat shield separates. So at that point, we will know carrier that it's there, and we should see Doppler from the parachute deploy. MRO will get the full extent of the EDL coverage from before entry until after landing. But as Doug mentioned, that's a store and forward system. And so the data will be returned to Earth about 3-4 hours later and made available to the project at that time. The Odyssey, the Mars Express data will, very much like the X-band, be kind of a carrier signal, and it will disappear about a minute before we land because it also goes over the horizon. Odyssey will depend on what happens to the Odyssey orbit as a result of the decisions that the program and NASA will make. In the baseline, it was to continue to receive data and forward it to Earth to a few minutes after landing. And in the modified system, we will see what we will see. We should see confirmation of Odyssey comes back about an hour and a half to 2 hours later, overflying the landing site. And so we should see at that overflight, we should get telemetry from the lander that indicates the lander state and whether or not it landed successfully.
Next question from Kennedy.
Riverson, Florida today. Just for Pete to clarify, if MSL is landing at 1:31 a.m. Eastern Time on August the 6th, given your current communications issues, can you tell me what the first time Eastern would be that you would expect to know whether the spacecraft survived or not?
That depends on whether or not Odyssey is moved in its orbit. If the program decides to position Odyssey back to its correct position, and that is successful, and MSL transmits UHF successfully, and Odyssey receives it successfully, then we would expect to hear at 10:31 Pacific 1:31 on the 6th Eastern Daylight Time that we have landed successfully. The times we give you are Earth receive times. The one-way light time is 13 and a half minutes. If Odyssey is not able to be moved and it still remains late, that means that it will fly over the spacecraft after the spacecraft has landed, and we presumably will be able to see transmissions from it. And that once again depends on what the program decides to do and the ability of MSL and Odyssey's telemetry system to work. It would be somewhere between 10:35 and 10:40. 1:35 and 1:40.
Todd, did you have a follow-up?
That kind of laid out the history this century of Mars exploration and what's coming in the future. I know that you're in the middle of a rephase of the Mars exploration program as a result of budget issues. Could one of you guys give us an idea of what future missions might be out beyond Maven, and when the next time when the U.S. might land another lander beyond MSL on the surface of Mars. Thanks.
Todd, we're going to toss it over to Dr. John Grunsfeld to start, and Doug may have a follow-up. John?
Thanks for the question. We're in the process of replanning the Mars program beyond Maven with our Mars program planning group. That's something that's run out of the Mars exploration program. Orlando Figueroa is helping us with a community-based science community, engineering community, and the general public to look at many different options, and they will present us with those options, and we will work that then through our NASA planning process. So we're very hopeful we'll be able to recapture the Mars program starting in 2018 and with many exciting missions in the future.
Okay, we're going to now go to the center that where it's all happening. They designed, built the rover, managed this mission, and they're going to get a lot of folks coming to this location, the Jet Propulsion Laboratory in Pasadena, California. We have questions. JPL?
Hi, this is Sally Rail with the Planetary Society, and a question for John. I've learned from the last 9 years of covering MER that planning is essential, but planning is also useless, as Dwight Eisenhower said. And I wonder, given that caveat, if you can talk a little bit more about the immediate plan going forward once wheels turn, and if you can get a little more into the specifics about what minerals you're going to be looking for given orbital imagery. Thank you.
Yeah, we do exactly what you say. That's our whole basis. This is a mission of discovery, but I think it also puts us into the new era of Mars exploration, where we step on the shoulders of all this data that came before us, and it would be a crime to not postulate and propose hypotheses in advance of our exploration that could help guide our exploration, and we're going to do that. So we see this image with this red feature in it that is our first indicator of what's in the landing ellipse. So far, all the other orbiters that have looked for hydrated minerals of the type that occur in Mount Sharp, those would be sulfates, those would be clay minerals. Those are the primary targets for our mission. But what's really interesting about this feature that we're going to land on is that it does have a different look to it than what's around it. We don't know exactly what it means, but to give you an intuitive sense for it, it's kind of like when you walk by a building early in the evening and you notice that it's kind of warm next to the building. That's what this is telling us, that relative to adjacent areas, this place just stays warmer later at night. And so there are a number of different options there, and one of them is that the rock retains a lot of heat because it's very dense. And there could be a couple of ways that would work out. Our most attractive, exciting hypothesis is that maybe water flowed through the materials there and precipitated minerals. If it did, we don't know what those minerals are. But that's a great thing about Curiosity, is that we'll be able to figure that out while we're actually checking out the instrument. So after about a month or two, depending on how things go, we're going to approach one of these features, and the first thing we're going to do is sample the soil. And the soil is important because from every mission beginning with Viking, it is a feature that is globally distributed around Mars, and it has about the same composition. You look at a Viking chemical analysis compared to Pathfinder, compared to MER. We knew there was sulfur in those soils going all the way back decades ago. But this time around, we're going to figure out what minerals are actually in that soil, and it should be really exciting because it'll be our one really global sample of Mars that we'll get with Curiosity. Then after that, we're going to approach an outcrop, a rock outcrop, and try to drill it. And when we drill it, we're going to pass the materials into the ChemIn instrument and into the SAM instrument. And as we check out those instruments, we're also going to be getting back science data that will tell us what's there. This, to me, is the really cool thing, is because from orbit, we don't really know exactly what's there, and so we have a chance for a discovery of a material that nobody can really put their finger on right now. And then after we're done with that, we will hit the road and work our way towards the lower reaches of Mount Sharp, where we'll begin to explore these clay minerals and sulfate minerals and the other geomorphic features there that suggest the presence of water. And from that, advance our hypotheses beyond just saying sulfates and clays equals water. We'll actually figure out the environment in which they formed. And then from that, we'll ask if this was the kind of environment that might have also supported microbial life. That's the way that the mission will work.
One more question from JPL.
Yes, Gordon Tokumatsu at NBC4 in Los Angeles. Scientists, engineers, and even journalists sometimes speak in the abstract about the discovery of water and life on Mars. I was wondering if any of you gentlemen can talk about the real implications of this in terms of future space exploration and even indeed the future of the Earth.
That's a pretty big question, and it's hard to predict how everybody will react. And certainly, going to Mars, one of the main reasons for going there is to figure out whether or not life ever started there. And the one big implication would be if in the second place in our solar system that we think life has a possibility, and it actually did start there, my conclusion would be that life is easy. It's a natural process, and that the universe is just littered with places that have life. And I think that would be a pretty spectacular finding.
Is there a follow-up? Okay, let's now go to San Francisco, to the Ames Research Center for questions. Ames?
Morning, gents. Wayne Friedman here with ABC7 News in San Francisco. This is really a three-part question for you. What is your batting average for Mars landings? Then I'd like you to elaborate on what necessitated the use of the sky crane in this incident. And would this be a method you might consider for a manned landing later on?
Well, I'll start, and you probably may help here.
Okay.
See, batting average for landed missions, I don't have off the top of my head. As Earth versus Mars, if you will, for all the missions we've sent, we're right around 40%, 35, 40%. So Mars wins most of the time, which is why this is a tough business. Sky crane, why do we need the sky crane? The airbags for Spirit and Opportunity, now I'm in your territory here, Pete, but you know, we were about, the mass of Spirit or Opportunity with its landing equipment was just about at the limit of what that airbag design system could handle. This mission was always conceived of being a more capable system, and to be able to do that, more instrumentation is required. And as an example, we have about 75 kilograms worth of instruments and 10 of those instruments, whereas Spirit and Opportunity have about 10 or 15 kilograms. I'm sorry, five instruments and about 10 or 15 kilograms worth total. So that kind of capability moved us out of the airbag arena, and we had to come up with another method of doing this. Sky crane made sense because if you put the engines and landing systems underneath it and you want to rove, that becomes a problem. You also don't want to drive around the surface with all that excess weight. So those were some of the concepts. We needed a different system because we were really at the maximum of the previous landed systems. And would you repeat your third one for me? Oh, humans, never mind, I got it. Human capabilities. We are just scratching the surface with MSL at a metric ton. When we talk about humans to the surface, we're talking 10 metric tons and above. The sky crane system, while from a technique perspective may have some promise, this system cannot put humans on the surface. We're pretty close to the metric ton capabilities about what we'll get. Could it be a great system for landing supplies, whether it's food or water, medical supplies, things like that, in a pinpoint or high precision fashion? It certainly could be a workhorse like that. But for the human systems themselves, I don't think it's capable.
Okay, before we go to the phone lines, we have a number of media, not only on the phone line, but at the centers and various other locations. I doubt very seriously if we will have the time to get to all of the questions. We'll try to extend for a little while, but please, if we don't get to your question, please call my office or any of the folks at the Jet Propulsion Laboratory, and we will get you folks on the phone as quickly as possible today for any follow-ups. But we'll try to get as many as we can before we have to sign off. So going to the phone line is Dave Perlman from the San Francisco Chronicle. Dave?
Oh, yeah, hi. A little difficult here, but that's okay. Just one question, and that is, on Mount Sharp, or within the landing ellipse, wherever you land, what do you anticipate being the maximum maximum degree that MSL will be able to climb, if it climbs at all?
The spacecraft is capable of climbing up pretty much close to 30 degrees. It depends on the surface it's on. It does worse in sand than it does on rock. That certainly, there's very few places, very few places inside the landing ellipse that have those kind of slopes. As to Mount Sharp, I'll let John answer.
Yeah, I'll just add to that when Gale Crater first began to float as a viable landing site, I looked at it and said, how in the world are we going to climb up the mountain? And so we got a task force set up to look at exactly at that question. And we did a series of simulations with the engineering team, the guys in mobility, to find paths that we could feel very secure and comfortable in, would get us up to where we need to be going. And we've got multiple routes up there that keep us on the kinds of slopes well below the margins, that limits that Pete was just talking about. So we're excited to get there and explore these routes. And if one doesn't work scientifically, the great thing is we can go down and pick another one.
Next caller is Kelly Beatty from Sky and Telescope. Kelly?
Hey, thanks. This is a question about Marty, the descent imager. Apart from the thumbnails, how long will it be before you get the full-blown, all the high-res back? And how will those images inform your early scientific and movement decisions?
Well, let's see. We will play the images back, starting from the bottom up, and then key segments of the descent. I think it'll probably take us a few weeks to get back all of the images at high resolution. I think that's probably about what it will be. I'll let John talk about how it will inform the roving decision, but I would like to point out that we actually have already tremendous photography coverage of the entire landing ellipse because of HiRISE on MRO. And so, John.
Yeah, I'll just say that there is some redundancy between Marty at a distance and HiRISE. I think the part that will be most valuable scientifically are the images that are acquired just a few meters above the surface, 10 meters, 5 meters, because those will give us a perspective of the surface at a level of resolution we will not get from any other instrument, HiRISE and the science cameras included, just because of the elevation that you get. So what they're really going to give us, in addition to the thrilling movie that I'm sure it's going to be, is the context in which to place our initial observations, and that's something we've never had before.
Next, we have Craig Covalt from Aerospace America. Craig?
Next, we have Craig Covalt, Aerospace America. Hi, this is Craig Covalt. Can I ask a question of John Grotzinger?
Go ahead, Craig.
John, please don't be shy about answering this question. But everyone pretty much agreement that the U.S. space program needs help, needs a boost. How will its success help the U.S. space program as a whole?
Geez, no pressure, Craig. Yeah, I think we all feel this incredible sense of pressure on MSL to do something grand and profound. And my feeling about that is it's going to be what it's going to be. We have done everything possible to pick the best sites. This was a process that was led by the community that went on for 5 or 6 years. We started with almost 100 candidates. We whittled it down to a final 4. We picked one of those that we think's a good mate for our instruments on this mission. And I think it's going to be thrilling. Personally, I just can't imagine being disappointed scientifically, even if we don't find carbon, even if we don't find, some feature that somebody might choose to represent a strong indication that not only was it habitable, but there may have been life there. In ascending Mount Sharp, we're going to go through the major eras in the environmental history of Mars that give us the basis for comparison to our own planet. And if you ask the question about how life got started on Earth, how it evolved on Earth, what were the trigger points that bring us to the evolution of animals and eventually humans, you always ask, well, what happened if those events didn't occur? Is there some place that you can compare to where that didn't happen? That's Mars. So even in the case that life was never present on Mars, I still see it as an extraordinary opportunity to get a bearing on our own existence on Earth.
The next call is from John Mangles from the Cleveland Plain Dealer. John?
Yes, hi. This probably is for Michael Meyer, but anyone on the panel could take it. I'm wondering, given what we know about the penetrating depths of cosmic radiation on Mars, what's the likelihood that you're going to find complex organics? When in the mission would you begin to do that? And are there any unambiguous biosignatures of life, anything that would compel you to say that you definitely have got ancient life, extinct life on Mars? Or do you expect you would be more cautious, assuming you found complex organics?
Okay. Yeah, the radiation environment on Mars is pretty severe. And so one thing you have to worry about is ultraviolet, but that only goes kind of skin deep. So in terms of preserving organics, it's not a real problem. What you're really worried about are galactic cosmic rays, and those will penetrate beneath the surface. And you do have a problem with those breaking down complex compounds into simpler ones, and eventually you end up with something that's not recognizable. So the trick is what you do is you find a rock surface that's fresh. And that way, what is exposed or near the surface that you can reach with a drill has only been exposed for a shorter period of time compared to when the rock was actually formed. So there is some hope of finding complex organic compounds if they're there. The other part is that some compounds, as they, quote, get weathered by these, you will end up with something that is organic compound. It's just that you're not able to decipher what it used to be. But it still tells you that the compound or compounds used to be there. I think I've forgotten the latter part of the question, but if you want to repeat that, unless I already answered it. Undisputable biomarker. That is an extremely difficult one. For one thing, the scientific community by nature will in fact have to dispute any organic compound that's found and argue whether or not it is a biosignature. But the other part is you can get many organic compounds formed naturally. And so the hard part would be finding the organic compound would be difficult, but then trying to decipher whether or not it's from biology or whether or not it's a product of physical chemical processes will be a debate. And we saw a good example of that in the Mars meteorite ALH 84001, where we found reduced organic compounds, and then the debate was how are they formed? Because you can make organics without life.
Okay, we're going to take a couple of more questions before we close it out here. We're going to now go to Brian Berkstein. I hope I got that last name right, from Technology Review. Brian?
Yes, you got it right. Thanks, Dwayne. This question came up a little bit ago about, for example, whether you could use this landing method for a manned mission to Mars, and the answer was that for example, that you couldn't. Maybe you could use it for supplies, things like that. More broadly, could someone sum up how much this mission will advance the knowledge that NASA feels we have or need to have in order to get people to Mars?
So there's two pieces of this we can address that I think are directly applicable. One of them is scientific, and I'll let Michael talk about that. But I'll talk about a technical issue we have with this, not an issue, but a technical capability we have with this. We have, in partnership with the Human Exploration Organization here at NASA, actually fully instrumented this heat shield and back shell. So we'll be collecting probably the most high fidelity information we've had on entry systems to date. So we'll be able to tell exactly how much of the heat shield is ablated away as we enter. We'll understand what the pressures are and temperatures are. And since it's guided entry, the angle of attack changes, and so we'll understand how that applies across the front of this heat shield, not just a single temperature or a single pressure. And there's some back shell measurements as well that help us with pressure. These kinds of data sets are extremely important in constructing entry, descent, and landing profiles that will apply to building larger systems that are capable to send humans. I'll let Michael talk about an instrument that we have aboard that was also supplied by the Human Exploration Group.
Yeah, thanks, Doug. The instrument is RAD. It's a radiation detector, and it's a broad range sensing instrument that is specifically designed to get a handle on what kind of damaging radiation would be at the surface of Mars. And the reason why you want an instrument like this is that although you have a good idea of what the radiation is in space, what happens to is that as the radiation goes through the atmosphere is that you generate what they call secondaries. So you can, in fact, generate other high energy particles that are actually more damaging than the original radiation itself. So RAD, the radiation detector, will in fact give you a good idea of what species are generating, what the radiation environment at the surface of Mars. And with that knowledge, then you can go about figuring out how to protect astronauts when they go to the surface.
Our final question comes from Leo Antright from Irish TV. Leo?
Thanks very much, Dwayne. As a TV man, I'm interested in the pictures, and I just wondered, I heard Pete talk about black and white in days 1 to 3. Is that worst case? Can we expect to see color pictures earlier? And more specifically, I'm being asked by editors all the time, what are we going to see? This mountain is bigger than the tallest mountain in Europe. Can you describe for us in more detail what television we can expect? What are these cameras going to produce? Is it going to be like the Rover on the moon landings, where Captain Video was able to move the camera around and look at things, or is it going to be more like the MSL, the Mars, the earlier Mars rovers?
Well, it'll be much like the earlier Mars rovers. The data is collected in pre-pan sequences, so we'll be doing panoramas, so you'll see basically that kind of panorama like you've seen from Spirit and Opportunity. They're very high resolution cameras. They certainly are better than high definition, at least the science cameras are, with basically full and natural color this time. I think that the cameras, I'm not that conversant with the optics of them, but I think that they'll be very good. The frame rate for the descent imager is certainly capable of doing a movie, if you want to do a movie, an 8 frame per second movie. The black and white photographs will be very good resolution. I don't think you'll see them as low resolution, but they will be black and white. The first color image will be taken from the MOLLE, the camera that's on the arm that basically is designed to look at rocks in a very close, high-resolution setting. That camera does have excellent optics features at infinity, and it looks out the side of the arm. The one thing we can't control is the orientation that the rover lands in. So if that's your first color picture, and if it happens to be pointed at the mountain, we'll get a great picture at the mountain, and if it happens to be pointed the other way, we'll get a great picture at the rim, et cetera, et cetera.
Okay, we are going to wrap up here. And before I toss it to someone who really knows about countdown clocks, Dr. John Grunsfeld, to give us the latest on the count, I want to remind folks come take this journey with us. Follow us on social media, Twitter at Mars Curiosity, Facebook, YouTube, all the social media out there. It will be an incredible conversation, incredible products. Also, for more information, www.nasa.gov/Mars and www.nasa.gov/MSL. We've seen the education and public outreach products, but make no mistake, ladies and gentlemen, this is serious business. If there's one thing to take away from this, this is the hardest mission ever attempted in the history of planetary robotic exploration. It is real. Come go with us, the team is ready. And now, the latest on the countdown to John Gunsfeld.
So if you want to know how long until landing, go to worldwideweb.nasa.gov/Mars. 20 days, 11 hours, 25 minutes, and 41 seconds. Thank you very much.
Good job. Great job.